All right, let's talk about understanding language. I mean, really understanding it, the context, the nuance, like we humans do,
Yeah, it's a huge challenge.
and trying to teach that to a computer,
Yeah.
especially when the field's moving so incredibly fast, it's really something.
It absolutely is. And, every now and then something comes along, some research that just shifts everything.
Exactly. And today we're diving deep into one of those moments. We're looking at a really key paper, BERT, Pre-Training of Deep Bidirectional Transformers for Language Understanding, came from Jacob Devlin and his team at Google AI Language.
Ah, yes, BERT. That paper and the model it introduced really did change the game for a while, redefined state-of-the-art in NLP.
Definitely. So our mission here is pretty straightforward. We're going to unpack this paper. We want to get a handle on what BERT actually is, the big idea driving it, how it learned.
And crucially, why it did so well, why it hit those amazing results on so many different language tasks.
Exactly. We want you, listening, to walk away with a really clear, kind of concise grip on this big step forward. Okay, let's unpack this paper.
Sounds good. So maybe we should start with the world before BERT.
Yeah, context is good. What was happening then?
Well, the idea of pre-training language models wasn't new. People knew that training a model on tons and tons of text first gave it a kind of general language sense.
Like a foundation.
Precisely. A foundation you could then build on or adapt for specific things like figuring out how sentences relate or picking out names in text.
Makes sense. Build a base, then specialize. So what were the main ways people did that?
There were basically two main camps, two strategies. First, you had feature-based approaches, think Elmo.
Right, Elmo.
With Elmo, you'd pre-train these contextual word representations.
Representations that knew about the words around them.
Exactly. And then you'd plug those representations in as extra features to whatever model you build specifically for your task.
Like adding pre-made smart ingredients to your recipe.
That's a great analogy. Then the other way was fine-tuning. OpenAI GPT was a big example there.
Okay, how is that different?
With fine-tuning, you pre-trained a whole model like GPT. But then for your specific task, you didn't just use features from it. You actually took the entire pre-trained model.
The whole thing?
Mostly, yeah. And you'd fine-tune almost all of its parameters, just adding maybe a small, simple layer on top for the final task output.
Ah, okay. Fine-tuning sounds, I don't know, more integrated maybe.
It often was.
Yeah.
And it was proving really powerful. But, and this is key, the sources point out a big limitation with many of these earlier models, especially the fine-tuning ones like GPT.
Which was?
They were largely unidirectional.
Meaning they only read text one way, like left to right.
Pretty much.
Yeah.
Or sometimes they might stitch together a left-to-right pass and a right-to-left pass. But it wasn't truly deep simultaneous conditioning on both sides of a word throughout all the model's layers.
Okay.
GPT, for example, used a standard left-to-right transformer.
And why is that limitation a problem? Why does seeing both directions at once matter so much?
Well, think about how we understand language. If a word is missing, or you're trying to see how two ideas connect or find an answer in a paragraph.
You look forwards and backwards from that point.
Exactly. You need the full context. A
Yeah.
unidirectional model is always kind of looking over its shoulder. It doesn't get that deep, integrated view of what's coming up and what just passed simultaneously, layer after layer.
Okay, I see.
The paper explicitly says this was suboptimal, particularly for things that need precise understanding right at the word level, like predicting a specific word.
Ah, okay. Right. So here's where it gets really interesting then. How did BERT get around that? How did it break free from just looking one way?
That's the heart of it, BERT.
Mm.
It stands for Bidirectional Encoder Representations from Transformers.
Bidirectional, right there in the name.
Yep, that's the core differentiator.
Hmm.
BERT was specifically designed from the ground up to pre-train deeply bidirectional representations.
So not just left then right, but somehow both, all the way through.
Exactly. It jointly conditions on the left context and the right context at the same time in every single layer of the transformer network. It's fundamentally built for that two-sided view.
Okay, wow. That sounds like a significant shift.
It was, and the outcome was this really powerful, contextually rich model. The paper showed that because of this deep bidirectional pre-training, you could take BERT, add just one simple output layer.
Like for classification or something.
Yeah, exactly. Just tack on a simple layer, fine-tune it a bit, and boom, state-of-the-art results on a whole bunch of different NLP tasks. And critically, without needing big custom architectures for each task.
That's impressive.
The paper sums it up perfectly. Conceptually simple and empirically powerful.
Simple idea, huge impact. Okay, but how? How does it actually learn that deep bidirectionality? That seems like the tricky part. If it can see in both directions, how does it avoid just, seeing the answer it's trying to predict?
Right, that's the clever bit. BERT doesn't use traditional language modeling for pre-training. Instead, it uses two specific, unsupervised tasks. It learns these tasks on just massive amounts of plain text. Books corpus and English Wikipedia were the main sources.
Two tasks. Okay, what's the first one?
The first is the Masked Language Model, or MLM. This is how they get bidirectionality without the model cheating by seeing the word it needs to predict.
Masked. Like hiding words, you cover some up.
Exactly that. During pre-training, they randomly pick about 15% of the input tokens.
That's 15%?
Yeah, 15%. And they mask them. Sometimes they replace the word with a special mask a token. The model's job is then to predict what the original word was in that masked spot, using only the surrounding words, the ones to the left and the ones to the right, as context.
Ah, okay, so it's like a fill-in-the-blank puzzle, but the clues are all around the blank.
Precisely. The paper mentions it's similar to the closed task from linguistics.
Yeah.
And they did something smart with the masking, too.
Oh.
To make sure the model worked well later during fine-tuning, when there aren't any mask tokens. They didn't always replace the chosen word with mask. About 80% of the time they did. But 10% of the time they replaced it with a random other word.
A random word. Why?
To force the model to rely on the context even more, to sort of double-check if the word it sees makes sense there. In the final 10% of the time, they actually left the original word in place.
Huh. So sometimes it sees mask, sometimes a wrong word, sometimes the right word, but it still has to predict the original word based on context.
Exactly. It forces the model to build a really robust understanding of context to make its prediction, not just learn a simple rule like mask means guess a word.
That's clever. Okay, so that's MLM for deep bidirectionality. What's the second task?
The second task is next sentence prediction, or NSP.
Next sentence prediction. Why add that? What does it do?
Well, MLM is great for understanding context within a sentence, right? Word, relationships, local stuff. But lots of important NLP tasks need the model to understand the relationship between sentences. Think question answering, you have a question sentence and a passage sentence. Or natural language inference, judging if one sentence logically follows another.
Right, understanding connections across sentences. MLM doesn't directly teach that.
Exactly.
Yeah.
So for NSP, they feed the model pairs of sentences, let's call them A and B.
Okay.
Half the time, sentence B is the actual sentence that came immediately after sentence A in the original text. We call this the is-next case.
Makes sense.
The other half of the time, sentence B is just a totally random sentence grabbed from somewhere else in the text corpus. The not-next case.
Okay, so real pair or fake pair?
Yep. And the model's job is simply to predict, is this an is-next pair or a not-next pair?
Seems straightforward enough. Did it turn out to be important?
Yes, the ablation studies they did later, which we can get into, show that this NSP pre-training really did help, especially for those tasks that need sentence pair understanding. So MLM and NSP together, those are the two unsupervised tasks that let BERT learn those deep bidirectional representations.
Got it. MLM for in-sentence context, NSP for between-sentence relationships. Okay, so BERT gets pre-trained using these two tasks on tons of text. Then what? How do you actually use it for something specific, like classifying emails or finding answers in documents?
And that's where the elegance of the fine-tuning process comes in. It's remarkably simple, which was a big part of BERT's appeal.
Simple how?
Because the pre-training did such a good job capturing general language understanding bidirectionally, you basically just take the pre-trained BERT model.
With all its learned weights.
Exactly. You initialize your task model with those weights. Then you just fine-tune all the parameters end-to-end using your labeled data for the specific task.
You tweak the whole thing.
The whole thing. And usually you only need to add one very simple output layer on top.
Like what kind of layer?
Depends on the task. If it's classification, maybe just a simple linear layer. If it's question answering, maybe a layer to predict the start and end tokens of the answer span. But the point is, you don't typically need to design complex, task-specific model architectures anymore.
Wow. So the heavy lifting is done in pre-training, and adapting it is relatively minor.
That's the idea. The underlying transformer architecture, with its self-attention, is flexible enough to handle single sentences or pairs of sentences fed into it.
Wait, how does it handle pairs? If you just stick two sentences together, how does it know where one ends and the next begins, or which part is the question and which is the context?
Good question. They use special tokens and embeddings. For any input, they stick a special CLS token at the very beginning.
CLS for classification.
Right. For tasks where you need one vector to represent the whole input, like sentiment analysis, The final hidden state corresponding to that CLS token is used. When you have sentence pairs, like for NSP during pre-training or for QA during fine-tuning, they put a SEP token for separator between sentence A and sentence B.
Ah, a divider.
Yep, and also at the very end of the whole input. Plus, they add learned segment embeddings to each token, basically telling the model, this token belongs to sentence A or this token belongs to sentence B.
So it learns to distinguish the two parts.
And position embeddings, of course, tell it where each token is in the sequence. All these embeddings, the token embedding, the segment embedding, the position embedding, get summed up for each token at the input layer.
Okay, so special markers and learned embeddings help it sort out the structure. And fine-tuning this whole thing, you said it wasn't too bad. How fast are we talking?
The paper reports that fine-tuning is relatively inexpensive. On a single GPU, maybe a few hours. On a cloud TPU, maybe even just minutes for some tasks.
It's nits. To adapt the model with hundreds of millions of parameters.
Starting from the pre-trained checkpoint, yeah. That's a massive practical advantage compared to training these huge models from scratch for every single task.
No kidding. That combination of power and efficiency.
Mhm.
Yeah, I can see why it took off. Let's talk about that power of the results. The paper claims some pretty big wins, right?
Oh yeah, the headline claim was state-of-the-art results on 11 different NLP tasks.
11. That's a lot. Covering what kinds of things?
A real mix. They showed huge improvements on the GLUE benchmark. That's the General Language Understanding Evaluation. It's a suite of 9 different tasks testing various aspects of understanding.
Okay, GLUE. How much better was BERT?
The paper mentions BERT pushed the overall GLUE score up by 7.7 percentage points absolute compared to the previous best. That's a massive jump on a diverse benchmark like that.
Wow, yeah, over 7 points is huge. Any specific tasks stand out?
On multi-NLI, which tests natural language inference basically, understanding logical relationships between sentences, BERT got a 4.6-point absolute accuracy boost. And notably, both the base and the larger BERT models beat previous systems, like OpenAI GPT, across most GLUE tasks, even ones with not much training data.
Interesting. What about question answering? Squad is usually the benchmark there.
Right. On Squad V1.1, where the answer is guaranteed to be in the passage, BERT's ensemble model set a new record F1 score.
Okay, beat the best.
And maybe more impressively, on Squad V2.0.
That's the one where the question might not have an answer in the text, right?
Right.
Much harder.
Exactly. On Squad 2.0, a single BERT large model blew past the previous best published system by over 5 F1 points. That showed a real leap in dealing with those unanswerable questions, which is much more like the real world.
Yeah, knowing when not to answer is critical. That's a huge improvement.
Definitely. And one more swag. That's a common sense reasoning task where you pick the most plausible continuation for a sentence.
Okay.
BERT large just crushed the previous baselines there too. Massive accuracy gains over models like eSIM plus Elmo and even OpenAI GPT. We're talking like 27 points and 8 points better, respectively.
Wow. Okay, those numbers really do paint a picture. It wasn't just a small step. It was a fundamental jump on many different fronts. But why? Was it just that BERT was bigger? Or was it really about that bidirectional thing?
That's exactly what the paper tried to figure out with its ablation studies.
Ablation studies, where they take things away to see what breaks.
Sort of, yeah. They systematically removed or changed parts of the BERT setup to isolate what contributed most to its success.
Smart. What did they find?
Okay, first, they tested the importance of that next sentence prediction task, the NSP. They trained a version of BERT without it, just using the masked language model. Performance dropped significantly on tasks like QNLI, a question-answering NLI task, MNLI, and even Squad 1.1. So that confirmed NSP wasn't just redundant, it was actually adding value, teaching the model something important about sentence relationships.
Okay, so NSP motors. What about the big one, bidirectionality?
Right. They compared their standard MLM-trained BERT, which is inherently bidirectional, against a model trained only left to right, like GPT, using a similar setup, but without the masking trick enabling bidirectional context.
The head-to-head. Bidirectional MLM versus unidirectional LTR. The results.
The unidirectional left-to-right LTR model performed worse, across the board on all the tasks they tested.
Worse everywhere.
Yep. And the gap was especially big on token-level tasks, like Squad.
Which makes sense, right? If you're trying to pinpoint the start and end of an answer span in Squad, only seeing the words before that span really handicaps you. You need the context after it, too.
Exactly what the paper argues. That deep bidirectionality is crucial for tasks that need context from both sides. They even tried adding a Bill STM layer on top of the LTR model during fine-tuning.
To try and give it some bidirectional capability later on.
Yeah, it helped a little on squad, but still didn't match the MLM model, and it actually hurt performance on some of the GLUE tasks.
Wow, so that was pretty conclusive evidence. The way BERT was pre-trained using MLM to force deep bidirectionality was fundamentally important. It wasn't just about using a transformer.
Correct. The pre-training objective was key.
Okay. What else? Did they look at model size? BERT base versus BERT large? 110 million versus 340 million parameters.
No.
Did bigger just mean better?
They did look at that. And yes, the larger model, BERT large, consistently performed better than BERT base across all the tasks.
Okay, bigger is better. Not too surprising, maybe.
Well, what was interesting, and they noted this in the paper, is that the large model gave significant improvements even on tasks with very small amounts of labeled training data.
Really? Like tasks with only a few thousand examples?
Yeah, like the MRPC task. You might think a huge 340 million parameter model would just overfit like crazy on such a small data set.
Right. Too much capacity for the data.
But it didn't. It still improved things substantially.
Yeah.
The hypothesis was that because they were fine-tuning the entire model, even on small tasks, the model was effectively leveraging the incredibly rich general-purpose language representations learned during pre-training on billions of words.
Ah, so the power came from the pre-training knowledge, which the large model captured better, not just from learning the small task data itself.
That seemed to be the takeaway. The pre-training was so effective that its benefits transferred even to low-resource scenarios.
That's a really cool finding. Did they check if you could still use BERT in the old feature-based way, like Elmo?
They did. They ran an experiment on named entity recognition ConLL 2003 MR. Fine-tuning the whole BERT model gave the best results, as expected.
What?
But just extracting features from BERT's hidden layers specifically, they tried concatenating the vectors from the last 4 layers and feeding those into a simple Bill S10 plus CRF model. That also gave very strong competitive results.
So almost as good as full fine-tuning.
Pretty close, yeah, only slightly behind. It showed BERT was flexible. You could use it as a powerful feature extractor if you wanted or needed to, even though fine-tuning the whole model usually worked best according to their experiments.
Okay, this has been a fantastic breakdown. So bringing it all together, connecting back to you, the listener, what's the big picture takeaway here? What did BERT really teach us?
I think the paper really hammered home that deep, unsupervised, bidirectional pre-training was a game changer. It showed you could create a single, powerful language model using transformers and clever objectives like MLM and NSP.
A model that understands context really well.
Exactly. And then you could take that single model and adapt it effectively and pretty efficiently to a whole bunch of different downstream tasks, even tasks where you don't have much labeled data.
Which means, for practical applications, models got way better at understanding language, more like humans do, seeing the whole picture.
Right. The aha moment wasn't just build bigger models, it was about how you pre-train them. That specific combination, the transformer architecture plus the bidirectional objectives like MLM and NSP, that's what unlocked that next level of contextual understanding.
Yeah, the objectives were the key to really harnessing the architecture's potential.
And what's still fascinating looking back is that finding about large models helping even small tasks, it showed just how much knowledge could be packed into those pre-trained parameters if the pre-training was done right.
Definitely. So thinking about how critical those specific choices were, bidirectionality, MLM, NSP, it really makes you wonder, right? What other ways are there to pre-train these models? What other kinds of objectives or architectural tweaks might unlock even deeper language understanding down the road? What angles haven't we thought of yet?
That's the multi-billion parameter question, isn't it? It's what keeps the field moving forward. An excellent thought to ponder.
Absolutely. Well, that feels like a good place to wrap up our deep dive into the BERT paper, a truly influential piece of work. Thanks for joining us as we unpacked it.